And we're back. It's time to sort it out with Mr. Swartout. Another problem involving work here. Now we are kicking it up a notch by including friction. Still, the force that we're applying here is parallel to the displacement, so there's no angle to consider. We want to find the work done by tension, the work lost by friction, and then the final velocity. Finding the work done by tension, let's just use W sub t for that. That's going to be the force of tension times the distance. Pretty simple there. Then for friction, let's remember what we know about friction. Here we're going to be dealing with kinetic friction because we're sliding across the table. So it'll be mu sub k times the normal force. We are on a level surface, so the normal force will be equal to m times g. That'll be our expression for the force of friction. Then that friction force is going to work over the entire distance. So we'll take our friction force, multiply it by the distance, and then that would be an expression for that. Then let's use work energy theorem once again, like we did in a previous similar problem. So net work being the change in kinetic energy. So what we can do is, the final kinetic energy will be the speed at which the box is going at the end, and what's going to determine that would be the net force times the displacement. So we can do the tension force minus the friction force. That'll be the net force over the entire distance that it goes, and then we multiply it by the distance. We can do a little work on that formula, rearrange a little bit, and get an expression for the final velocity. Something else you could have done was you could take this work done by tension, subtract the work done by friction, and then that would be the net work, and that, in other words, that could go on the right hand side here. You could set that equal to the final kinetic energy. So either way works, and that's what you need for this one.